Here. So welcome everybody. This is Unit 3, Lesson 2. So usual deal, please go look for the tasks to complete for U3L2. Should be under assignments or on the Canvas homepage on the weekly calendar. Today's date is November 13th. It is Friday the 13th. Who should you look out for? Anyone know? Who might be coming for you on Friday the 13th?
Freddy.
Yes, watch out for Freddy. So if you haven't seen that horror film, you should check it out. It's a lot of fun. All right. Here we got a few more people coming in now. Noah, how you doing? Maybe we don't have audio yet. Noah, are you there? How things going?
Pretty good, how are you?
Doing good. Looks like you have a video pulled up on that huge screen above you.
Yeah, YouTube video behind me.
Nice. Brandon, how are things?
I'm doing pretty good, Mr.
You,
Hurt.
you get the belt on your board fixed?
Yeah.
You should try to invent one that would last better. You could probably make a lot of money if you copyright it with the company or something, so they don't break as much.
That's a good idea.
All right, kiddos. We're going to start off as usual with a couple rounds of breakout discussions. Make sure I have the right task to complete open myself here. I was working on another class. All right, random question. Throw it in the chat right now. Question for today is, what is the weirdest food you've ever eaten? Give you 20 seconds to think about it, then split you into rooms. All right, rooms are open. We'll come back together in about 2 minutes. So, great. Okay, I once again owe you an apology. I've been spending a lot of time planning the new unit in this class, as well as 2 of my other classes that I'm currently teaching. I have not had time to grade your tests. I'm hoping to do that this weekend, so you should see grade reports pop up over the weekend for that. So just keep an eye on Canvas, but sorry for not having that ready for you today. Next on the docket was just homework review. Both assignments are looking pretty good. Just to share my screen here. You had to make sure you completed the Bob Gardner reflection. So I assume you got the graph done. Again, looks like everyone got pretty consistent data that pressure just dropped. That's not surprising, but what's weird is that the temperature got colder, but then it warmed up a little bit. It was still below freezing, but it got less cold, I should say, as he was rising. And then you had the Hewitt reading reflection. Again, this is looking great. I'm always struck by this graph here, just showing you the layers, and this is something we're going to learn about today. But was Bob Gardner even close to space?
No, not really.
Yeah, not at all, which is crazy. When you watch that video, you can see the curvature of the Earth. You think he's got to be right there. And they even call his mission like a mission to the edge of space, but that's not actually. He did travel through most of the gas in our atmosphere is in those first 2 layers, troposphere and stratosphere. It's pretty thin after that, but it's not technically space. So anyway, I just think that's kind of interesting. Any other big questions or comments or anything you got stuck on the homework assignments? Sophia?
I had a question about the mesosphere. When if a spaceship exits the atmosphere and has to go through the mesosphere, how does it withstand the heat? Oh wait, the thermosphere actually.
Yeah.
How does it withstand the high temperatures of 500 Celsius to 1500?
Good question. It's pretty baffling to see those temperatures. My understanding is that isn't necessarily, even though they measure that as the temperature, it's not necessarily what it would feel like, because it just means that the gas molecules, there's very few of them and they're moving really, really fast, but they're spread out. And so I don't think that if you were to stand in that area that you would instantly burn up. But it's a good question. I don't actually honestly know. I'm still very surprised because if you look at that curve, it goes way, way up into extremely high temperatures. So you would think that anything going in there would burn up. Comets, asteroids, spaceships, when they do hit our atmosphere, they do experience a lot of fire and burning, right? They have to have a heat shield. But I don't think it's that isn't because of the hot temperatures. It might be, but I think that's just because they're going so fast and they're hitting all those gas molecules. And so the friction is creating the fire. So it's a good question. I'm kind of baffled by it too, about those such high temperatures in that upper part of the atmosphere. You'd think you would just burn up the minute you got up there, but I think there's something weird going on there with just that there's so little gas up there, and these molecules are moving around super, super fast, but they're really, really spaced out. But I don't know. It's a good question. Not something I can fully comprehend either. That was a good one. Any other questions? All right, then next on the docket was just going to use some brief slides here and some poll questions to review content, make sure we're feeling good, and then we'll do a little Ed puzzle about Bob Gardner's Descent. So give me 1 second to share my screen to my iPad here, and bear with me. So just be ready to answer a couple poll questions that I'll throw into the screen. I know we haven't done this before. It's kind of like an Ed puzzle, but live. All right, I want to make sure I have the right slides here. Okay. Should be good. All right, I'm going to hide everybody's tabs here. So can I just get quick verbal confirmation everyone's seeing the atmosphere in front of them right now?
Yeah.
Awesome. All righty. So the reason I have a picture of a bowling ball there, which seems kind of random, is just to emphasize how thin the atmosphere is compared to the size of our planet. If you think of Earth as a bowling ball, the atmosphere would essentially be as thick as that sort of lacquer or sheen that's on the surface, right? Which is pretty mind-boggling to think about. But that's where all the gases are being held, and they're being held to the surface of the planet by gravity, just like gravity is holding us to the surface of the planet. We're going to explore in-depth climate in particular, but it's good to understand weather is the day-to-day conditions, right? This is something that can change rapidly throughout even just a 24-hour period. Climate is more like the weather patterns, right? So it's a more general trend, right? What's the average annual rainfall? What's the average annual temperature, or average temperature month by month, or something like that? Both of these things can change, but climate's going to be a much more gradual change. Weather, again, could change within a 24-hour period. Within a single day, you could experience multiple forms of different weather. So there's a whole bunch of different spheres that we use to classify Earth's surface, right? The biosphere, which is where living things can be found. The lithosphere, which is when you get underground and start looking at the layers of rock and magma, which we'll learn about a little bit later. But we're going to focus right now on the atmosphere. Let's talk about the gaseous surface first, and then we'll start delving deeper down. This came up in a previous question too, but most of the air you breathe is actually a totally innocuous gas, nitrogen gas. It's actually N2 because it's a diatomic molecule. It's not flammable, it's not explosive, it's not poisonous. It's actually perfect gas. It's completely inert, doesn't react with anything. Plants can need it, but they have bacteria that help remove it from the air for them. Only 21% of the air you breathe is oxygen, which seems low, but our lungs are evolved and adapted to collecting oxygen efficiently at that percentage. And that's honestly a good thing, because oxygen is very explosive, very volatile, right? If it's exposed to any kind of accelerant, it will ignite, right? And so if we had higher concentrations of oxygen, if you ever tried to light a cigarette or something, you'd blow your face off. So we don't want too much oxygen in our atmosphere. And then it seems crazy. I mean, it's about 1% or less of everything else: carbon dioxide, argon. You find argon in light bulbs, methane gas, water vapor, all that kind of stuff. Okay, first poll question to throw at you. Should be on the screen right now. Give that a go. And again, just take your best guess. I'm not grading these or anything like that. And this is also anonymous. Alrighty, got 13 responses. Here are the results. Good. Most of you are getting that, the key distinction, right? Rain one day and sunshine the next is weather. That's very rapid change. And the average annual rainfall of 18 inches or something like that, that's a description of general climate. So just try to keep those straight in your head. Alrighty, moving on. So the atmosphere is composed of multiple air molecules, and this creates what's called air pressure. This is a really important concept to understand. Sometimes referred to as atmospheric pressure. I prefer to just refer to air pressure. Oh, hold on. Sorry, my screen has frozen for some reason. So let me share this again. I don't like that it does that sometimes. Seems like the poll questions seem to freeze the computer side of it. There we go. Once again, everyone's seeing the atmosphere and air pressure on their screen? Give me a verbal confirmation.
Yeah.
Awesome. All right. So air pressure is essentially the weight of the air weighing down on top of you. I know it's a weird thing to think about, right? But if you imagine a little stick figure standing on this curve right down here, right? On top of that stick figure is all of these layers of air, right? And again, we don't think of gases as weighing very much, but they do weigh something. And so that's what air pressure is essentially coming from. And it's from these air molecules colliding with you, right? And you can feel this if you just wave your hand in the air right now. You can feel the air around you because those air molecules are colliding with your skin, and you're sensing them by moving the hairs on your skin and so on. And air pressure can change. If I had a little stick figure that climbed up this curve and got a little higher, notice that there are now less squares of air on top of this person. So that person would be experiencing a lot less pressure, smaller amount. Bob Gardner made it up this high to about 40 kilometers. And so he was experiencing much less air pressure, and I'll talk about the consequences that had on his balloon in a bit. But again, just keep this key idea in mind, right? Air density decreases as altitude increases. So here's a little measure, here's altitude going up, and you can see that low down, all these air molecules are packed closely together, whereas higher up, they are much more spaced out. And again, this is entirely due to gravity, right? Remember, gravity is pulling all things towards the center, and air molecules respond to it too. So most air molecules are found compactly lower down, and once you get to higher elevations, there's less of them. So internal pressure usually has to come to some equilibrium with external pressure, right? And so we are evolved to our bodies, the air that's inside your ear canals and things that your inner ear, the pressure within that matches the pressure outside. And this is why when you fly in an airplane and go up to high altitude, you're experiencing less air pressure, so the air inside your inner ear expands, and that makes your ears pop. It's also why scuba divers, right? Scuba divers who dive down underwater, they experience a much higher amount of pressure. So that's what makes your ears hurt when you try to swim to the bottom of a pool, because it's crushing that inner ear space. Divers in particular can have a lot of different problems that air molecules can dissolve into the blood more readily. And if a diver comes up too quickly, it becomes gas bubbles in their blood, right? It's called the bends. That's not a good thing you want to experience, but it's all because of that relationship between internal and external pressure. If you watch Bob Gardner's video again, you can see this happen with his balloon, that when he started off on the ground, the balloon really didn't look all that inflated. But once he got up to 39 kilometers of elevation, the balloon looked like this, right? Absolutely massive compared to that tiny little capsule. And that's because there's a lot less air pressure when he was much higher up, and the balloon expanded to a much, much greater size. Okay, next poll question. Should be on the screen now. Give that a go. Interesting. Can you all read the full sentences? My view, it's the sentences get cut off.
We can read them.
Yeah, you can see all the text. Interesting.
Yeah.
I have like a little tiny window. I guess it just cuts the text off. Hey, all right, we got 13 responses. Okay, here are the results. Interesting. We're a little torn here. So why do your ears pop when you are in an airplane flying at 33,000 feet or 10 kilometers up? Again, my sentences are cut off for some reason, but the correct answer, which I think most people selected, is that lowered air pressure causes the air in your inner ear to expand, right? There's less pressure outside, so the pressure inside the gas is going to expand out, and then it kind of pushes past your eardrum. That's why your ears pop a little bit. All right. Any other questions or comments so far? All right, just 3 more slides. Bear with me here. So let's talk about the layers of the atmosphere, right? What do we split our atmosphere into? There are 4 specific layers: the troposphere, the stratosphere, the mesosphere, and thermosphere. So the troposphere is the important one because that's where we all live. This is where life exists. It's the closest to Earth's surface. It's actually quite thin, right? It's only from 0 kilometers to 12 kilometers in elevation or in height. But temperature and density of the air is really thick, and so this is like a nice warm layer where water can exist in liquid form or gaseous form. And as you rise up in the troposphere, so let's say you're on your way up, the temperature is going to decrease, right? Things get colder, and we know this, right? If you were to go stand on top of Mount Everest right here, that's where you're going to see snow and ice, and it's going to be really, really cold. The next layer up is the stratosphere. It accounts for elevation levels 12 kilometers to 50 kilometers, so it's a little bit thicker than the troposphere. There's a drastic decrease in density. This is where the ozone layer is. This is where O3 exists, and it's an important layer for protecting us from some of the more harmful forms of radiation that come from the sun. UV light in particular, it gets absorbed at that layer. And as we witnessed with Bob Gardner, as he was rising through this layer, temperature actually warms up a little bit because you have ozone absorbing UV light and other forms of solar radiation. Again, it's still below freezing. It's still super, super cold, but the temperature is going to be actually warming, right? It's just getting less cold as you travel up through that layer. So this is the same text, it's just a better diagram showing all of it together. And again, I want to emphasize, and I think I have it on the next slide, but Bob Gardner only made it to about here, right? So that's why they called it the stratus jump, because he was jumping from the stratosphere. So let's now talk about the next 2. This again is where I'm still I try to wrap my mind around this too, but the mesosphere right here, the 3rd layer, accounts for 50 kilometers, 80 kilometers of elevation. There's no solar radiation absorption for some reason, so it gets very, very cold. I'm not sure if it's just because there's no carbon dioxide or because the gases become so thin at this point that nothing really warms up. But then once you hit the thermosphere, and again, think of that name thermo, right? It means heat, temperature, that kind of thing. This accounts for most of our atmosphere in terms of elevation, right? It's really, really thick, but it's the least dense. So there's not very much gas here at all. But for some reason, and Sophia asked a good question about this earlier, the temperature just spikes hugely. And again, I'm not entirely sure what's causing this or what's going on. It might just be that it's proximity to solar radiation, right? So lots more sun is coming in and there are some gases that absorb that. It might be because there's just so much space and the gas molecules start moving really, really quickly. But again, about 90% of the actual gases that make up our atmosphere are located below the ozone, right about there. So that accounts for about 90% of the gases that are present in our atmosphere. And so all of this is really, really thin, not dense at all. Okay. Final poll question. Should be on the screen now. Try it. All right, just waiting on one response. There we go. Alrighty. Here are the results. Very good. All of you are going with no. So yeah, we can't fly balloons into space, else we'd be doing that a lot more often. But the reason for it actually is due to the buoyancy. That the air just becomes so thin that there's no gas that has a low enough density that would allow a balloon to continue to rise. The balloons, every balloon will eventually reach its maximum sort of height that it can achieve, and it will just stay there, or eventually, I think bursting is also usually a problem, though we are able to make balloons that are pretty large and pretty strong. I think what the limiting factor eventually would just be a lack of buoyancy, right? And I think this is one reason why Bob Gardner, again, got about as high up as he could in a balloon, and then jumped from there. So what's interesting is I think that is the safest way to reach heights like that, right? Versus trying to jump out of like an airplane that trying to fly it in air that thin would be really hard. That's why the spaceships that we send into space have to have huge rockets on them, because you're not going to be able to use a jet engine, anything with a propeller on it, to get you through this air, because again, it's super, super thin, right? You need something that's going to provide its own thrust. All right. Hopefully that was helpful review. Any questions or comments on those slides? All right, then the next task is, now that we've discussed Bob Gardner's ascent and looked at the layers of the atmosphere, let's take a look at his descent, right, and his drop. So I've got a little Ed puzzle there. This is on tasks to complete step number 4. Please select the Science2A. This is A period. So Science2A Bob Gardner descent Ed puzzle. It's about 3 minutes long, but I have a whole bunch of questions in there. And so I'm going to time for 10 minutes to get through this. So I'm hoping it won't take 10 minutes to complete, but I'll keep an eye on people's progress. And once we have enough responses, we'll come back together to review. As usual, if you can't get the Ed puzzle to work, I have the original video on YouTube posted in a bullet point at the bottom under number 4. And there is a Google form that has the exact same questions. 10 minutes, go for it. Let me know if you need help. And I think he has said that I don't think he wants to try this again, because he experienced so much G-force. So that's literally amping up the amount of gravity his body was actually experiencing, or simulated gravity, that idea. His heart couldn't pump his blood around his circulatory system for a little while there. Thankfully, though, he achieved that right at a point where he was going to transition between zones. So he recovers, and you might notice that as he's recovering, his airspeed starts to drop quite significantly, right? He was going like 800 miles per hour, and then suddenly he drops back down to much lower levels. And so the final question, you'll notice the sound also, at least I think, and again, we're a little torn here, but the sound should have gotten a lot louder. You heard a lot more kind of air sounds and whizzing sounds in that final bit. So why was there sort of this sudden moment where his airspeed dropped? Did he deploy his parachute? Was that what did it? Do you think it was his parachute? Did you see his parachute come out of his back? Wasn't his parachute?
What was the question?
So why did his airspeed slow down so much? Like, why is he not going as fast anymore? So Daniela.
I said as he gets closer to the Earth, the more air drag is on him, and so the slower he's going to go. Very
good. In fact, there's a key moment where essentially he exited the stratosphere and entered the lithosphere, right? Where we are troposphere. I keep mixing these up now, but yes, he entered that other layer where air density is much higher. So a lot more drag started to act on him, and that slowed him down. It reduced the amount of G-force he was experiencing. So he wasn't going to faint or pass out again. So again, just a little demonstration of the layers of the atmosphere he was going through. Good. Any other questions or comments on that? All right, kiddos. We are obviously going to focus now specifically on the innermost, the closest layer. And again, I'm pretty confident when I say troposphere, it's a troposphere, because that's the layer that we live in. That's the layer of the atmosphere where life exists, and where all the cool kind of actions happening with weather and climate. And so I want to introduce you to something that are called climographs. And you might be somewhat familiar with these. I'm not sure if PSI covered any of this stuff. But a climograph is essentially a graph that is sort of a snapshot of the general climate of an area. So here's a graph showing you San Diego, California. And you'll notice there's two things. There's a red line. That red line is showing you the average temperature per month. So there's the average temperature for January, average temperature for February. All of that lines up with the temperature in Fahrenheit on the right side of the graph. The green bars on the bottom are representing the the monthly precipitation, which is snow, rain, any of that stuff in inches. And so you can see that in San Diego, January, February, March are very rainy months, and it gets pretty dry in June, July, and August, right? So it's kind of just a nice little snapshot of the general climate of an area and what's going on in that troposphere. And so you can look at different parts of the world and see both differences and similarities, right? These are all essentially desert environments. So notice precipitation is super low in all of these places. I guess Australia is a little higher, but also interesting to see the inversion in weather patterns, right? So notice that in the Northern Hemisphere with Kazakhstan and Chad, you have very hot summer months, right? May, June, July, and August are very hot. But then look at Australia. It gets really, really cold in May, June, July, and August because they're in the Southern Hemisphere where seasons are essentially flipped. And you're going to be reading a little bit tonight about why that is. But this is why I like climographs, because they give you a really quick snapshot and a really nice way of comparing differences between certain locations, just looking at average temperature and precipitation by month. So you're going to be doing a little worksheet. You're going to work with a partner, and you're going to be analyzing these two. It's a San Diego climograph and then a mystery city. There's a little quiz on the tasks to complete. This is the final one. Step number 5 is what we're on right now. So I'd like you to, we just went through the slides. I'd like you to click on that climograph worksheet part 1, and I'm going to throw you in breakout rooms with a partner. And what I'd like is for one of you to be the reader. So you're reading the questions and the instructions out loud so that your partner can hear. The other person's the timer and is going to keep track of time as you work through this. So I'm going to throw 10 minutes on the clock. Let's set for 10 minutes just to see how much progress we can make. You don't have to be done in 10 minutes, so don't panic or don't try to rush, but just keep track of time and try to get through each question steadily. I'll be here listening. If you have questions, you can drop back in, but otherwise everything should be pretty straightforward. So timers, 10 minutes on the clock. Breakout rooms are open. We'll come back together in 10 minutes. Go for it.